Hi, and welcome to the second section of inferences surrounding means. Um, and this part two, what we're going to look at is when we don't know the standard deviation. And it's really the important thing to understand is what I mean by that is a t-score versus z-score. So a t-score is, in a sense, a fudge factor from we don't understand what the standard deviation is given a problem that we're dealing with. So example, if we are taking SAT scores, we know what the deviation of SATs are. They announce them every year. The average is around 1,000 and the deviation is around 200 for the SATs for students across the country. So we know what that deviation is. IQ scores are similar. A lot of standardized tests, they know what the standard deviation is going in. When you come into a lot of other realistic situations, and the reason why I wanted to really cover T-scores in this, is there are other situations where you will not be able to understand what the standard deviation is. The first problem we're going to look at is going to be an example of speeds of cars. If we're talking about how fast a car is driving in a certain speed limit, we don't know what the standard deviation is. We never will know, but we can use the standard deviation from the sample that we take. And because it's risky and that standard deviation can always change, we go to a t-score and it becomes, in a sense, a fudge factor to work with the fact that we don't know what the deviation is. It can change, and we widen it up a little bit. The conditions will remain the same, where we're going to be looking at a random sample, no more than 10% of the population, and the data should be nearly normal. So this really hasn't changed much from hypothesis testing when you understand the deviation. What I want you to take a look at first is this problem. So pause the video, just take a minute to read through the problem. Hopefully you had time. And in this problem, you notice again, it's dealing with cars. And we're trying to see whether or not the average speed is really above 30 miles an hour. You can see from this, there's people above, people below. We're going to run a significance level of it. The conditions, okay, we're going to assume that the cars were randomly selected. We sampled definitely less than 10% of all the cars that are on that road at any given moment. And we're going to, and we already looked at the data to say it's nearly normal. Now, what did I do for that? Well, I put the data on here. And again, I'm going to sort it. And I noticed that I have some in the 20s, a lot in the 30s, and then none, very few that are high up. So I can assume that this is a nearly normal model. So that's all that I'm looking at. It doesn't have to be, ultra, intense just to show the nearly normal. It just has to be somewhat normally distributed. You don't want to have a whole bunch of 20s, no 30s, and a whole bunch of 40s. That would not be normally distributed. Now, when it comes to the hypothesis, again, hasn't really changed much. The average speed of cars is 30 miles. The average speed of cars is greater than 30. That's what we're trying to show. We're trying to see if our average and deviation are significantly different to show us greater than 30. So we're going to run a t-test this time of means using a significance level of 5%. I would strongly suggest when no matter what course you're doing, no matter where you are, indicate what type of test you're running, whether it's a t-test or a z-test. It helps someone try to understand where you're getting this information from. Were you using it from your sample with your deviation, or were you, using a deviation that was given to you? So all of that, if you notice, hasn't changed much, which is why this, in a sense, is a review. The only thing that really has changed is the fact that we're using a t-score, and it changes the mechanics a little bit. So I'm going to scroll back up here and look at this problem. And where it changes the mechanics is if you look at this data, I need an average and a deviation. If you want to do hypothesis testing with means, deviation, unknown calculator, again, I just typed something and I even spelled deviation wrong. And, this pops up and you can just click here and enter the information as you see fit. The one issue with doing an online piece, an online software like this, typically is that you need to calculate the average and standard deviation. The way I'm going to do this on my graphing calculator, if you have one, it doesn't require that. But any of these online sites will require you to actually put in information. So real quick, I'll go to the side. If you have the information in, you just type in equals, write the word average, parentheses, click on A, and this will give you the average. So right away, we see the average is slightly higher than 30 miles an hour. Standard deviation, hit equals, STDEV for standard deviation, and click on here, and now you have a standard deviation of 4.4. Now again, that is the standard deviation of our sample. which is why we're going to use a t-score. So these would be the data that you would enter for a t-test for a population. What I am going to do is I'm going to show you what it looks like on a graphing calculator. It's more often used, or not in real situations, but in educational situations, this is pretty easy, where you can just click on stat, go to edit, put the numbers in the list, and I'll show you what to do from here. So now that I have the numbers on the list, what you're going to do is, again, you're going to run a stat. You're going to run a test, and you notice the first two are the z-test and t-test. Now, all of these are different tests you can run with the same idea where you're looking for a p-value. We're not going to get into all of them in this course. We just don't have the time. So the one proportion z-test was last unit. The first thing we do is a z-test when you understand what the deviation is, and then there's a t-test when you don't know where you got the deviation from the sample. So this one, we got the speed of the cars and the deviation of the cars from the t-test from the sample. So you go to data. We're trying to determine whether or not this is 30 miles an hour. We want to see whether or not we were above 30 miles an hour, and then we're going to calculate. Now I had to actually back up because my data was a little off, but here is the t-test. Again, we're going to take the data. We're seeing if it's different from 30 miles an hour. We want to see if it's greater than 30 miles an hour, and we're going to use the list one that we created, and we go to calculate. And again, no matter where you go, you would probably get the same you should get the same p-value. And there's a 31.4 and the 4.42, which we got from here. So you can do it on Excel and then put it into, say, a website that will do this, or you can just do it in one step on the calculator. It doesn't really matter which way you go through it, but the idea is that we're looking for the p-value. So in this case now, we get a p-value of 0.06. So this information you'd want to take down into your mechanics section. And again, we have a p-value is equal to 0.06 and all the other information you want to enter there. So what can we draw for a conclusion? Pause the video, see if you can put the conclusion.